Okay. Well, good afternoon, everybody. Next week, same place here. Next Thursday, we'll hear from Jennifer Chubb, who's a professor of computer science at the University of San Francisco. And she has a peculiar hobby that she wants to tell you about. And the hobby is keeping up with quantum computing. So that's next week. Today I have the distinct pleasure, truly honor of introducing you to somebody who soon will not need any introduction. John Aycock from the University of Calgary in Alberta, Canada. He wrote a book about games, playing games on computers, and he's going to tell us about those games and a lot of other stuff. So let's welcome the speaker.
Good afternoon, and thank you for coming. Appreciate the opportunity to come and tell you a story. I'm going to tell you a story today. And the way that this story begins is with this. This is my first computer. This is a Commodore PET 2001-8, where the 8 refers to the 8 kilobytes of memory it had on it. What may not be obvious from the picture is that this case is actually made of sheet metal. This thing weighed a ton. And if you undid the screws on the sides, you could actually open it up. It was this clamshell design. You could open it up, and it was so heavy that it actually had a prop rod inside, just like you have on the hood of your car, so that it wouldn't come crashing down on your head while you were working inside. Now, I'm not telling you about my first computer because I'm a narcissist. Although, don't get me wrong, I am a narcissist. But that's not why I'm telling you about this. This actually leads into this whole story. So, for me, the Commodore PET was eventually upgraded to this Apple II. And the first game console that I had at home was one of these. This is a Mattel Television. And I picked one up a couple of years ago, and I'm pleased to say that there is still, after all these years, a reason why these game controllers consistently land up on lists of the worst game controllers ever. I'm not sure, it's a bit hard to see on these pictures, but you see those little bumps there? Well, that's what every game mapped the jump functionality to, and they're really hard to press, and so your hand cramps up after like 2 minutes of playing with this stupid thing. So, at this point, you can probably guess my age with a fairly high degree of accuracy. And you could say that I've been involved with retro games for a while. It's just, you don't call them retro games when you're first playing them. So when I went to university and studied computer science, this is what we used. So this is not a computer. This is a dumb terminal. And it is really just an interface that connects up to the real computer, which is big and draws a lot of power and is located in some locked room someplace. My point is this. These are all very constrained systems, very constrained development environments. And in contrast, when I go into our computer science labs now, the students there are in an environment much more like this. I'm exaggerating. But not that much. They'll have their dual displays and their laptop open beside them with access to all of the world's knowledge. And then, just for good measure apparently, I've never quite figured out why they do this, they have their cell phones out too. How many devices do you actually need? And then, in our low-level course, the most constrained environment that these students work in, they're using these. These are Raspberry Pis, and they fit into the palm of my hand. I apologize, I would have brought one with me, but airport security. And God forbid I should have tried to bring a clock with me. But you know, these, even in their most minimum configuration, have 512 meg of memory. So that means that if you're playing along in the home version of this talk, this thing now that our students use, it fits into the palm of your hand, has over 65,000 times as much memory as my first computer. 65,000 times. That's a lot. And you might think at this point that this is just some old curmudgeon saying, get off my lawn, you young whippersnappers. But you know, something very important has been lost along the way. And to explain what that is, I want to turn to the composer Stravinsky. Nah, actually, I'm just teasing you. That sounds way too academic and pompous. I want to talk about the guy who made this game, Halo 2600. So this is a version of Halo that runs on the Atari 2600. And it was developed by this guy named Ed Fries, who is VP of Xbox development at Microsoft. So this is the title screen for the game. This is what it looks like when you're playing it. There's your little Master Chief right there. This is what it looks like when you're about to get your ass shot off, because it turns out it's actually really hard to dodge the bullets and press the key combination to get a screenshot go all at the same time. So I didn't actually last too long in this. But what Fries pointed out is that really the same thing Stravinsky was saying, which is that there's this connection between constraint and creativity. And you find it in all these creative fields. So game development, music. I was actually reading an architecture book within the last 2 weeks, and they were saying exactly this. And really what they're saying is that necessity is the mother of invention. If you need to make something work badly enough, you will figure out a creative way to do that. So, what am I really talking about in terms of constraints? Well, turns out that my 8K machine was positively lavish compared to the amount of memory that the Atari 2600 had. These are not the scale, by the way. It's like, wow, these are really gigantic. So the 2600 had 128 bytes of memory. I did not misspeak, 128 bytes. I actually discovered a machine recently that even had less than this. So there's a really good book called Racing the Beam by Montfort and Bogost. And it's actually a very approachable book talking about the 2600 and a number of its games. Okay, I get it. There's no pre-reading for this talk. So if you haven't read it, here's kind of what it boils down to. So imagine, if you will, that this is your television screen, because back then you would typically plug these things into your televisions. And so what happens is an electron beam sweeps across the screen, and as it sweeps across the screen, it is drawing a line of the content that you see. And then that beam turns off and it returns back to the left-hand side. And then it turns on again and goes back to the right-hand side. And it goes back and forth. I'm not going to do all the lines. Until it gets down to the bottom. And then it goes back to the corner and does this again. 60 times a second. And as a result of this electron beam moving past, you see the game. Now, as computer scientists, when you program anything graphical, what you do is you say, okay, here's what I want displayed, and you place it into memory or you place it into a bitmap, and then magic happens, and the magic graphic fairies come along and render this onto the screen for you. So in other words, this is your mental model of what you're Well, back in the days of the 2600, memory was expensive. And so instead what happened, so that red dot represents the beam going across. And there was none of this memory. And so what you as a programmer had to do for each and every line of the screen is you had to tell that computer how to render each individual line. That was part of what your code had to do. And it had to do that before the electron beam got to that point on the line where it was going to show it. So in a very real way, you were racing this electron beam. In effect, it's like driving down the interstate and building the road in front of you as you're driving. And these weren't even the only constraints. I mean, you had the slow input and output. You had very small, very slow storage devices, so floppy disks, cassettes even. They weren't that big in North America, but certainly in Europe, cassettes were huge for software distribution. And the developers themselves had constraints. So if you were developing a game for a home computer that was constrained, chances were you developed it on that exact same computer. You didn't have any special stuff that you used. And if you're developing for the game console, you weren't that much better off. So this up here is an ADM3A, and it's the dumb terminal of the type that David Crane used to create this game down here. This is Pitfall, the Atari 2600. And not only did they have these constrained environments, and notice, by the way, the only thing got on here is text, and there's not a lot of it. But oftentimes these programmers, they'd also have to not only write the games, they would have to develop the tools for which to write the games, the assemblers, the debuggers. So it's like you aspire to drive down the interstate and build the road in front of you, but first you have to invent wheel technology. But yet, these guys were able to pump these games out in sometimes absurdly small amounts of time. So this is E.T. It was a famous example of this, and due to some epically bad decisions at Atari, it was forced out in 5 to 6 weeks. This one down here is Chase the Chuck Wagon. The developer wrote this in a weekend. And you might say, well, these are crap games. Well, there are actually lots of really bad games back then. Trust me, I've played many of them now. But when you consider all these constraints they had to work under and all these rudimentary development tools, even these so-called bad games could actually be pretty amazing that they got them done at all. This kind of lays out the background as to the conditions developers had to work under and the conditions games had to run under. I want to turn now to retro game archaeology. This, incidentally, one of the first known versions of Tetris. The lag was, oh my God, it's tremendous. So Ian Bogost wrote a book in which he said that we need more of what he called media archaeologists to find all these treasures. And so what would a retro game archaeologist be? What is retro game archaeology? Well, the way I define it is in terms of 3 T's. So here we'd be interested in the tools and the techniques and the technology behind the implementation of these old games. And taking all this and putting it in a broader technical context. So it's not just about saying, well, you know, E.T. did this. Okay, we're done. Let's go for lunch. No, it's about saying, well, E.T. used this one technique, and it was also used in Raiders of the Lost Ark, and it was also used in Congo Bongo. Incidentally, side note, as a student, you never imagine yourself standing in front of a room full of people talking about Congo Bongo. You just don't picture yourself that way. But finding out that all these games were using this technique, and what were they doing? Well, it was a particular type of bank switching. What is that? Well, it's a type of memory management. So it's contextualizing this whole process. And then bringing it forwards in time and saying, okay, well, what are these techniques used for now? Maybe it's in different places, maybe some of them are in more niche areas, but a lot of these techniques actually still have applications now. It's just, they're not things that are foremost in your education when you get taught computer science. And that's the thing. So why would you bother doing this? Well, you don't get taught this sort of material anymore. You don't work with these constrained systems, so you wouldn't necessarily see these old techniques for dealing with them. And if I were in the history department, I would probably say that the reason we should study this is because history is important. I'd probably say that, you know, holding a pipe, wearing a smoking jacket, and leaning on a mantelpiece, but okay, actually I don't know what happens in the history department. This is just my mental image of what goes on over there. And I don't disagree with that. You know, history is important, but I'm a computer scientist. I'm very pragmatic. And what I do know is that history is cyclic. And these things that we discard along the way, these are things that we will probably need at some point in the future. So for instance, you could say, well, as we did, as technology progressed, that, well, we have lots of memory now. Why would we be concerned about how to manage small amounts of memory? And then someone came along and said, hey, we've got these new things called cell phones, and by the way, they don't have a lot of memory on them. And then, of course, now we have smartphones, and they have lots of memory. So we don't need those anymore, except for the fact that we do. We have embedded systems, and we have the Internet of Things, and we have sensor networks, and guess what? These are all these same constrained devices. And I'm amazed that I found that picture. Rabbit on bicycle. Yay, Internet. So more importantly, why do it right now? So in Canada, we actually had a change to our copyright law recently. You have fair use down here, and we have had what's a similar concept called fair dealing, which is traditionally narrower than fair use. A couple of years ago, the copyright law changed, and so we actually now have clear exemptions for education and research. So it means that I don't get to see the inside of a prison anytime soon, so yay. Down here, the Internet Archive has actually been doing some amazing stuff. They've got some exemptions to the copyright law. And if you haven't been to the Internet Archive, they've put a bunch of this stuff online, and you can play tons and tons and tons of these old games in your web browser. If you haven't been there, go. Donate to them. They're doing amazing stuff, and you will lose like 3 weeks of productivity just going through all this. The latest announcement is that they got their emulation to the point where they can actually boot and run Windows 3.1 stuff in the web browser. So they got thousands of DOS games, Windows 3.1 stuff, whole bunch of these old consoles and old computers. can almost hear the bandwidth being sucked out of the room as I say this. But I do want to make an important distinction. So, retro game archaeology is not about playing games. I'm not a game historian. I don't care about what was the first or the best or had the biggest impact, because I'm interested in the implementation. Some of these examples, when you find them, they are in some fairly obscure places. And you have to come to terms with that. You can't get upset because this example you found wasn't in this well-known game. I mean, it'd be like you found a unicorn. You can't get upset because the unicorn pukes on your shoes. It's a unicorn! How many of these are you going to see in your life? Slightly more sobering reason is to do this now is that the people who did this work, they are not young anymore. And I've actually, just in the last few years doing this work, come across a number of instances where I go to look up someone to contact them and they have passed away. And in some cases, literally taking secrets to the grave with them because there's something that only they would have known. And on that happy note, let's actually look at how we would do retro game archaeology. So the first step is choosing a game, and there's a number of ways you can go about this. So you could use sort of a traditional lead finding methodology, by which of course I mean Google and Wikipedia. And there's lots and lots of people who invested insane amounts of time on their favorite games, and there's no reason not to leverage this effort. So for example, I was interested in games that used a data compression technique called run length encoding. And so I fed this into Google with some other search terms, and out popped this guy's blog that I'd never seen before. And he said, yeah, there's this game called Spook House, and I think it uses run length encoding inside. So, awesome. Am I done? Not quite yet. So back in the 80s, there was this guy down here. And he was fond of saying trust but verify. So in any academic endeavor, what you're really interested in are primary sources. Studying games, the game code is the primary source. So unless I've seen it in the game code, it didn't happen. So it's nice to have a lead, but there's still work to do. Now, something else I've had to do, happily not too many times, and that is basically a brute force search through different games. So sometimes I'll have kind of this tip that, yeah, I think some of these games did this one particular technique. And so essentially what you have to do in this case is set up your system, your emulator, to jump up and down and say, hey, we found this in action. And then you just start playing through one game after another. So I had to do this relatively recently. I was looking for a particular type of copy protection I was 99% sure should be in Atari 400 and 800 games. So what I did is I set up the emulator, racked up a bunch of games, and started playing them. And then had a few hits, and then I got to dig into their code and actually found a nice example to use. And there are actually not one but two magazines right now devoted to retro games. So this is another way to find leads. And so sometimes there'll be just like one sentence in an interview with one of these old game programmers. And it's like, that's the example I need. But again, I mean, I can't remember what I had for lunch yesterday. And expecting these people to remember the details accurately of code that they wrote 30, maybe 40 years ago and might not have seen since, it's asking quite a bit. And I do apologize because I only realized after I made the slides how wildly inappropriate it was to have memories fade right beside a picture of Reagan. So, yeah. Oops, sorry about that. Okay, so final way you might choose a game is just some sort of curiosity-based question. And so I mentioned I got it in television a few years ago, and I was playing the version of Pitfall on there. I was looking at it and saying, no, this looks a lot like the Atari 2600 version. I mean, a lot like the 2600 version. Wondering if it's the same algorithm used to generate the jungle in both of these cases. And down here, so this is, sorry, it's hard to see, but this is Yar's Revenge, and it has a nice colorful force field. And this is Laser Gates, which also has a nice random colorful force field. And I'm wondering, geez, same technique used to do both of these? Or in this case, I was playing through Super Mario on the NES, and was mid-jump with Mario, and in my head pops, gee, I wonder how the level information is stored. And there went Christmas. The answer is yes, yes, and it's complicated. All right, so you've chosen a game. Next step is to actually acquire the game. And I've shelled out some money to get some of these. Usually what it comes down to, I mean, it's very rare that you find source code for most games. Usually what it comes down to is that the Russians are awesome people and they archive so much material for us. Did I mention the research exemption for copyright? So you acquire this from wherever. And then you have to run it. And sometimes it's just simply not possible for certain types of obscure environments. And in any case, real hardware is not your friend at all. Really isn't. Because really what you want when you're doing this study is you want an omniscient view of the world. You want to be able to see everything, essentially be outside that game system in a lot of ways. So emulators are really the way to go here. And there's some great ones. So this is one called Stella for the Atari 2600, and it actually shows you all the details of everything that's happening there. And the memory is so tiny, it's showing all of it to you at once right here. It's all in that one little box. The flip side to this is that emulators suck. Oh my God. I have 4 Apple II emulators installed on my computer right now. And I've used an additional emulator because they all do different things and they're all broken in slightly different ways. And they aren't really designed for this type of work. So sometimes what I've had to do is modify the emulators or extract out data from them to look at in different ways. So this is a game called Parsec, which you can see up here in the corner. It has a scrolling background. This was on the TI-99 4A. And I wanted to figure out how the scrolling worked. Now the problem is that the TI-99 4A has this graphics chip, which has basically 2 memory locations where you do everything. And so I wanted to see what was happening inside it. So imagine trying to figure out how furniture is placed in a house, and you can only look through the mail slot. It's tough. So what I did is I gathered these data traces from the emulator, and I actually wrote this visualization which is showing me all of the memory in the graphics chip. And so I can actually see how the pieces are moving around. And this is It's impossible to see on here, but this is actually showing me each individual bit in that graphics chip. And if you wonder how big this is, there's me for scale. We have this cool visualization studio on campus with this wall that is literally just screen, and so I was able to throw it up on there and see everything all at once. It's really cool. The scary part is the real work hasn't even started. Yes, clowns, sorry. Okay, so this was just the prelude. So we figured out what to study, got it, figured out how to run it. Now we actually have to analyze it. Now, trying to figure out all the game code doesn't really make a lot of sense. There are diminishing returns because there's lots of code in all these games that's very samey, like it's going to initialize stuff, and really what I try and do is I try and go in with a question and say, this is what I want to find out about. And so it allows me to exclude a lot of stuff very early on. You can do this two ways. You can look at the code, so static analysis, and sometimes if you can't run it, this is your only option. Or you can do some kind of dynamic analysis, so trying to analyze things as the game is running. So this is, if you want an analogy, it's like trying to do a jigsaw puzzle where all the pieces can move around on you as you're trying to do it. Or like the Sudoku from hell. And as computer scientists, when you hear debates about, say, programming languages, you might have heard someone say that it's not just the language, it's the language and the library together. It really makes it. Well, here, it's really not the CPU, but the CPU and the platform. So in fact, all of these devices use some version of the 6502 CPU. But if I take the same game on, say, the Commodore 64 and the Apple II, it's going to look wildly different. Okay, so it's the same instruction set, but the graphics is done differently, the memory map is done differently, the I/O is done differently, the audio is done differently. And so it's not just about learning in a particular assembly language, you actually have to get all the tech references for a particular platform, figure out why this game is, say, storing stuff at 4,000 hex. Oh, it's because that's where the memory map graphics is. And you really have to dig into a lot of these platform-specific details. So there's the code, and then there's the data. So first of all, you have to find it. So where is it located in this binary blob? And then try and figure out how is this actually made sense of by the code. Does anyone see the pattern? Because this is usually what you start with, is just, here's a hex dump. This is the data describing the first level in a game called Load Runner. And if you ask the right question, the answer will just pop out at you. So what these are the platforms in the level. And here's another one, which is actually a bit harder. This is from a game called Mystery House from 1980. And I was actually thinking I was going to have to go through some long, painful analysis of this. And then in a moment of desperation, I just sat and thought, wait a minute, if I were to program this, how would I do this? Like, well, I'd be lazy, first of all, and I'd probably structure things in a certain way, and once I asked that question, all of a sudden, I had the structural elements that I could use to start breaking it down. Of course, you always want to test your hypotheses, and so emulators are, again, great for this, because, for instance, Pitfall, if I want to test my understanding of how the jungle is generated, what I could just simply do is pause the game in the emulator, pop into the debugger, change some values around in memory, and restart the game. And see, okay, does this match my expectation of what this should look like? Some games, though, are actually too difficult for that. And so what I've resorted to there is actually injecting data into them. And so, for instance, this is from a text adventure game. And what I convinced it to do is generate prime numbers for me. Because I was figuring out how the virtual machine that was inside the game was, how those instructions worked. I'm sure you're like, yeah, text adventure, whatever. Super Mario, though, is another game that I did this for. And so what I did there is created a version of World 1.1 that you have never seen before. And this is not a great level, nor is it meant as one. And all I'm doing here is I overlaid this data over top of level 1 so that I could play around with it and verify that I understood how all this level data was encoded. This goes on for a while because I never put the flag at the end to end the level. In some cases, for some games that had generic game engines, what I've done is I've actually created new old games. Because, among other things, it allows me to get a sense of what the environments were like to work in. So there are a bunch of systems for creating text adventure games. And what I've done in a bunch of these now is created what I call the telephone booth game, which is where you're in a telephone booth. Actually, that's pretty much it. You're in a telephone booth and there's a phone. So you're in a location, you have an object to interact with. And really that gives you a feel of how difficult these things are to describe. So this is all the description that goes into making this simple game with this one system. But it also allows you to compare across these different game systems and see how difficult and how expressive they were to work with. Now, reverse engineering is fun for the whole family. Try it sometime. Yeah, we could go see Star Wars, or we could do some reverse engineering and see how far you get. But there's some algorithms and things which actually turn out to be fairly difficult to understand what's going on. And so part of what I've done for some of these difficult cases are visualizations. And the thing about visualizations is you probably only need them once. Because as soon as you see the algorithm visualized, you basically just get it like that. And then you don't need the visualization anymore. But for some tough cases, it's actually a good way to create that initial understanding. So this is from a game called The Seventh Guest. And this is one of the first CD-ROM games that was on home computers. And these CD-ROMs were very old and very slow. And so they had to be using some sort of compression in order to get this from the CD-ROM into the machine and on your screen. And what I wanted to understand is what was this compression and how did it work? So I did this visualization. So each of the red squares you're seeing is a chunk of the image that is changed just in that one frame. The white means it has changed at some point during the sequence, and the green is just basically for positioning, tabbing out each block to where it belongs. And I actually thought this was going to be noisy, but as soon as I ran this the first time, I was like, holy cow, I can actually see what's going on here. And you can even see the bad acting that they were doing in this game. And there are thousands of these things in the game. So that's one. And they don't all have to be visually amazing. So this is figuring out an algorithm for maze layout from a game called Beneath Apple Manor. And it had some weird stuff happening with the basic code it was written in, and so I finally said, okay, I'm just ripping this out and seeing what this looks like as it runs. And yeah, what this is showing me in character form is the numbers of all the rooms and how the algorithm burrows through from one point to another. So yeah, as soon as I saw this, like, oh, okay, I get it. And the question mark is it actually doing probing, which is the part that was confusing me. Okay, time, I'll show you one more. So this is a visualization that I was using for copy protection on the Apple II. And this is showing you how the head for the floppy disk drive is moving as it's accessing the information. And these over here are stepper motors that could be accessed in the drive. So basically, as a programmer, you had complete control over the system, like down to where you're positioning the disk head. There's no operating system. It was all you, which was a blessing and a curse. If you want to do some weird copy protection, this was your system. It was awesome. So the other thing, which you've probably seen from time to time on, say, the History Channel, is these archaeologists doing reconstructions. And this is something that I do too, and it's really not a visualization which is trying to get understanding, but this is more checking to see whether I do understand something. And in these cases, what I do is I'd write my own code to take that game data and see if I can reproduce what that game looked like. So I have one, for instance, that regenerates all the Lode Runner levels. And it doesn't have to be pretty. If you've never seen Lode Runner, it actually looks better than this. Way better. But this gave me enough of a representation that I could compare this to the game and say, oh yeah, okay, I got it. I know what's happening here. The game Mystery House that I showed you before did actually look this bad. No color, it was just these sketches. And so yeah, another visualization. This is from one called The Hobbit. And if you notice some weird color artifacting, that was actually a lovely feature of some systems back then. And this is the ending screen from a game made by Scott Adams, not the Dilbert creator, different Scott Adams, who did a whole bunch of games. And this is what you saw when you completed the game. I have not actually completed the game. It was actually more fun and challenging doing this than playing the game itself, but whatever. And you've probably gotten the sense quite correctly that I've written a fair bit of code in order to do this, and yeah, I've had to build a lot of tools to do this. So disassemblers, I don't know if you've ever heard of what are called pretty printers. I said source is rarely available, and turns out that even when you get it, it can really look like rubbish. This is the source code for a game called Elite. Yeah. So there is no hope, and so what I did is actually wrote a pretty printer to actually make this much, much more readable. If you aren't familiar with 6502 assembly, you're just going to have to take me at my word that this is much, much more readable. But you can see, just because of the practices and the constraints at the time, there weren't a lot of comments in here. The labels are all very truncated. Branch if equal to O. Here's another label called Fantastic, thanks. So, what is retro game archaeology? Well, it's actually very hard technical work. So this is actually a systems level type pursuit. But there's lots of stuff to find. And the amazing part for me is that a lot of these techniques are still relevant now. And this is really the time to go do it. Thank you very much.
I was looking through the titles of the papers that you had written.
Oh dear.
And one of them was like current issues in ethics and computer security research. So I was wondering if you could maybe like touch on that. But just like as far as what are the concerns in ethics?
Well, of course, you can ask Dr. Solons about that too.
We only have 5 minutes, right?
I guess the 140 character version is that a lot of the guidelines for doing research are based on biological research and doing research with humans, and so there's lots of concerns that computers can introduce that really fall outside that scope. So for instance, if I want to create some malicious software, well, I'm not gathering data from humans, I'm not gathering data from animals. Should I have ethics oversight? I should. Am I required to? I'm not. And so that's just one of many of these cases where really you're operating at the fringes.
How are you feeling about emulation moving forward? Because I heard it used to be that because we'd have exponential increases in power needed to emulate, is that, do you think, still going to need to be the case moving forward, like for modern systems?
Yeah, so the question is about emulation moving forward. And emulation is actually really, really, really hard to do and get 100% right. So let me give you an example of this. So there are a couple of systems. So the Apple II is one of them, and there's also there's a Radio Shack TRS-80 system where I've come across this. I'm sure other systems did this as well. But when they had data on the bus, it actually got held on the bus slightly longer than it was supposed to, and there were some programs that actually knew about that and took advantage of the effect. So for instance, you could use that to figure out when vertical blanking happened on the Apple II, even though the circuitry was not designed to allow you to do that. And so getting stuff like that right in emulation and even knowing about it all to begin with is actually really hard. And yeah, so you do need a fair bit of horsepower just to make sure you can propagate all these weird little effects around at the right time and get everything synced up correctly between all these different subsystems. So yes, I have no desire to become an emulator author. I'm actually astounded by what they can get running in the browser. They're actually translating some of these emulators automatically with in scripting. They're translating it in JavaScript automatically. So, yeah, I would imagine moving forward that the line as to what we can and can't emulate will just sort of creep along after it.